Hello, welcome in this video to explain about urban logistics, which propulsion you can choose, either batteries, hydrogen or natural gas. First, an overall approach. There are different impacts on different scales, local or global. The climate change is mainly linked to anthropogenic greenhouse gas emissions, including CO2. This is an overall impact at the planet level. The pollutant emissions have a local impact. The impact is where the pollutants have been emitted. In terms of energy, this is available through many vectors, and it can undergo transformations from electricity to hydrogen, from coal to hydrogen, from solar to electricity, etc. What is most commonly used on Earth is fossil resources, but this is a finite quantity, and this quantity being used is always increasing. That means that there is currently no energy transition, but an addition. First the wood, then the coal, then oil, then gas, then hydroelectricity, nuclear, and renewables like photovoltaics or wind power. For urban logistics, all scales have to be considered. First, because the greenhouse gases emissions have a global impact, but with an indirect local impact. That means if local emissions create a global change on the climate, there will be local climate change in the city, for example, where the pollutants, where the greenhouse gases have been emitted. The pollutant emissions, it's a direct local impact. And about the energy, there is a worldwide growing competition for access to energy, especially decarbonized energy vectors. So this is an indirect and direct local impact. And currently, energy is mostly coming out from Europe. This is petrol, this is natural gas, uranium, and maybe we could imagine to have locally produced energy. How many vehicles are concerned? In France, about 7 million total commercial vehicles. Buses are quite rare compared to this high number. In the European Union, it is 40 million. And in Europe, it is 55 million vehicles. So what could be the criteria and how to compare it? First, the criteria could be analysis about the global life cycle. And it includes the manufacturing, the use, and the end of life of the vehicle. But it also takes into account where the fuel, the electricity, the hydrogen comes from and is used by the vehicle. The second criteria, very important, is how much it costs. How much for the purchase, for using it, that means the fuel, but also maintenance. And the third thing, which is very important, it has to be easy to use. So how to move from conventional internal combustion engines to alternative solutions like natural gas or preferable bio-natural gas, The second thing is the batteries. It's another solution. And the third solution is hydrogen. Here is a fuel cell, but you can convert hydrogen through many solutions, not only fuel cells. Each solution has some advantages and some disadvantages. For urban logistics, there is first light utility vehicles. And on this document, you can see that in 2030, we can compare CO2 global emissions for internal combustion engines on the left, with natural gas, not biogas. And when you come to pure electric vehicles with batteries here, or natural gas, in fact, that is biogas, you have a global CO2 emission that is very competitive. Hydrogen is not mentioned here because most commonly hydrogen vehicle is an electric hydrogen vehicle because hydrogen is converted into electricity on board the vehicle. For urban delivery vehicles, for example, 12 tons vehicles, the principle is the same and the result is the same. When you use a battery electric vehicle, you really decrease the CO2 equivalent emissions on the global life cycle analysis. And for biogas, it's also a very good solution, but it's not zero emission when you use it. But first focus on natural gas. And I would insist that biogas is a priority to reduce the CO2 results. Depending on different use of the natural gas vehicles, you can see here that natural gas vehicles have lower CO2 emissions than diesel vehicles. It's mainly due to the HC result, where this factor is 4 for CH4, the methane. Nitrous oxide are also very largely reduced, no matter it is biogas or natural gas. About batteries. A battery is a low energy vector, but a high efficiency vector to store and to propose electricity. About batteries, this is first principle. You can see here the e-motor, the power electronics, and here the battery. Here it is in the case of a fuel cell vehicle, but for a battery electric vehicle, you don't use it. So we could say, okay, but for batteries, the cost for the emissions to produce the batteries and also to produce the electricity are really poor in terms of CO2. So the global result is that battery electric vehicles are not competitive in terms of greenhouse gas emissions. In fact, here you can see that it is globally very, very low compared to conventional ICE. And if you compare in-use emissions, not global life cycle emissions for a BEV, with an electric mix of around 600 grams CO2 for each kilowatt hour, it is almost equivalent to in-use emission of an internal combustion engine, which would emit 100 grams CO2 for each kilometer. And this is very low. So we can say that currently BEV in use emissions are very low in almost every case, whatever the electricity mix. And here is a small reminder about the electricity mix in France, in the EU, and in the world. So in any case, BEV emissions in use emissions are competitive. Then hydrogen. Hydrogen is a high energy vector, but to convert it to a fuel cell or an internal combustion engine presents an average efficiency compared to batteries. A fuel cell uses hydrogen and air oxygen to produce electricity. It releases only water. About 50% of the energy included into the hydrogen is converted into electricity, and the rest is converted into heat. That can be converted and used for the vehicle and the passengers itself, especially in winter. So an hydrogen vehicle, in case of a fuel cell vehicle, is an electric vehicle that can be recharged in only a few minutes with a range of several hundred kilometers. Currently 500 to 600, but very soon more than 800 or 1000, that means 1000 kilometers. Here is the complete picture you saw a few minutes ago, but we had the hydrogen tank, the fuel cell, the power converter to adapt the voltage, and the rest of the classical electric powertrain. Here is a more technical overview of your fuel cell system. In a fuel cell system, in red you have the H2 loop. In green you have the air, that means the oxygen, and you can get from it electricity here, but you have also to take care about heat, and so you have to cool the system. In terms of global characteristics, hydrogen energy density is very high. You can see here that it is 33,000 watts per kilogram. Compared to gasoline or diesel, it is about 11 or 12,000. And for batteries, it is 150 up to 300. But hydrogen density is very low. And the problem is how to store it. 1 kilogram measures more than 11 cubic meters at ambient temperature and pressure. So H2 has to be converted. It can't be directly used. So it can be converted through a fuel cell to produce electricity. It can be produced through a turbine to produce both mechanical energy and also heat. But it can also used in conventional ICE, and many projects are being led today with large manufacturers in the world. The other thing is that H2 has been produced. That means it does not exist widely alone. In fact, it's often associated to other components. You can use electrolysis. You can use some thermal processes from biomass. Many solutions are being developed. The other thing is that fuel cell electric vehicles are not yet at large scale production. That means the costs are very high, like any technology at low scale production. And also this means that maybe you won't find available the vehicle you want. And the consequence is that the cost of the fuel cell vehicle is important for the moment, and also the hydrogen cost itself. So how to choose between natural gas, batteries, or hydrogen? For natural gas, you can say, okay, it's available. For batteries, it's the beginning for urban logistics. For hydrogen, it could be soon, between now and 2025. In terms of cost, natural gas solution is about ICE cost. For batteries, there is an extra cost for the new vehicle, and this cost is reduced in terms of global cost analysis because electricity cost is really lower, and also maintenance cost. For hydrogen, the cost is very high currently, but it's just the beginning, so that does not really mean the cost will remain high in the next years. Some manufacturers predict that in 2025 the price of an hydrogen fuel cell vehicle will be approximately the same of a plug-in hybrid vehicle. The question is also, is my vehicle zero emission? For natural gas, it's no, and for batteries and hydrogen, yes. For autonomy, it's not an issue for natural gas and hydrogen. For batteries, it's an issue. It's an issue because also the charging time is long. About heating, it's difficult for batteries, but for natural gas and hydrogen, it's not a problem. For refueling, it's limited for natural gas and batteries and very limited for hydrogen because it's the beginning. And there is an hydrogen plan in France, for example, but also in Europe. And we have some milestones that can make us see when suitable infrastructure will be available. But in many cities in Europe, hydrogen stations are already available. So why choose one solution or the other? For natural gas, this is a standard technology. And if emissions don't need to be zero, but just lower. If biogas is available, because if it is standard natural gas, not biogas, the life cycle analysis is not very good. And natural gas is a solution when extra cost or important extra cost is not possible. About batteries, this is a low maintenance technology. There is no noise, zero emission. The charging infrastructure is starting to be available, and if the charging time is not an issue, you can choose this solution. And also you can choose battery solution if autonomy is not an issue. So now why choose hydrogen? You can choose hydrogen when you need that the refueling time is the same than an internal combustion engine. And also if you need a long range compared to an ICE. If you know that in your region charging infrastructure is under preparation, when you will get the vehicle, the infrastructure will be available. As I told, there is a French but also a European plan to develop this hydrogen refueling station infrastructure. If you want to invest now directly to zero emission with a quite heavy and intensive use of your vehicle, you can invest directly to hydrogen, whereas the cost is really high. But because this vehicle will be still valid, for example, for zero emission area in cities in the future. If the TCO, including public funding, is acceptable, because currently, as the vehicle and hydrogen cost is quite high, there is public funding that is quite high. And if batteries, energy and power is not sufficient. So all solutions are quite complementary, and there is not a unique choice, but there is one choice for each strategy.